This is the last of our major gas laws, the Gay-Lussac's law. You know from your simulation that we were looking at the relationship between temperature and pressure. Remember, I'm going to go faster than you're going to write, so pause and get all the blanks filled in before you hit play again. Because we're looking for temperature and pressure, we have to have the amount of gas and the volume held constant. We haven't dealt with anything where the amount of gas has changed yet, and we won't. That will be saved for a later unit in the course, or actually probably in second semester. Okay, so the Gay-Lussac's law states that pressure and temperature are directly proportional. So again, you should have got a graph where you had your data points look like it was in a straight line, meaning that they are linear or directly proportional. As one goes up, the other one goes up at the same rate. Right? So if you increase the temperature and the particles start to move around more, well, in Charles's law, we wanted to keep the pressure the same, and so the volume increased. Well, if your gas is in a container where the volume can't change, well, then when you increase the temperature and the particles move around faster, they strike the walls of the containers more often and they increase the pressure. You can see you've got your equation down here. It looks very similar to Charles's law. And so we are just going to do two examples and you are set for your notes. So looking at the first one, if a container with a fixed volume, right, and that's important that the volume is fixed. If a container with a fixed volume with air that is at a temperature of 287 and has a pressure of 1.8 atms, so we know that that's our kind of initial temperature and pressure. It says, what must the temperature change to if the pressure is increased to 650? And the way that that's worded is kind of important. We can't change the pressure and cause the temperature to change. We can only change the pressure by a temperature change, right? The temperature causes the pressure. The temperature is the independent variable and the pressure is the dependent variable. It can't be the other way around. So we want to know, what is the temperature need to change to if the pressure is increased to 1,650 torr. Well, we got a one good thing, one bad thing. Well, the good thing is our temperature is in Kelvin, so we don't need to do a unit conversion there, but our pressure has to be in the same units, and it's not. It doesn't matter what we convert it to. We can convert it to ATMs or torr, doesn't matter. Also notice that our pressure of 1.8 ATMs is 2 sig figs, and so because that's the least out of all of them, our final answer will be the 2 sig figs. So I'm going to go through, do my unit conversion like we did a couple assignments ago, making sure that torr is on opposite sides of our fraction so they cancel. So 1,650 divided by 760 gives us our answer, and I'm dividing because that 760 is on the bottom of the fraction. Now notice here on this answer, I go to 4 significant figures. Right, remember, my final answer is going to be to 2, but I don't want to round this answer to 2 sig figs and then put it into our Gay-Lussac's equation and then round it again. So going 2 decimal places further than I need won't cause issues with rounding and rounding twice, but you can't round to 2 sig figs twice. So because I chose to list out the givens over there on the left, which you don't have to do, but you do have to show your work and then write down your equation and show more work. But looking at my givens, I place them into my equation where they go, right? We know that the P1 is 1.8, the P2 is now the 2.171, both in the units of ATMs. Our temperature one is 287 in Kelvin, which is what we needed in. So now because our temperature is in Kelvin, our T2 will also be solved in Kelvin. Remember on these, we need to cross multiply. So 2.171 times 287 gives me a long number. And again, notice I rounded it to 4 sig figs. We're going to divide both sides by 1.8 to isolate our variable of T2, giving us our final answer to two significant figures, right? T2 equals, say what you're solving for, and round your answer to sig figs and place units on the end. Now, notice there is no decimal here. That would make it three significant figures, right? It's just the 350, so it's 2. Last problem, what will the pressure of a gas sample at 82.1 degrees Celsius if its volume is held constant and when the gas is at a temperature of 15.2 degrees Celsius, the pressure is 204.3 kilopascals. So when the temperature is 82, we want to know what pressure it's at, knowing that when it was at 15.2, the pressure was 204.3. Now, our pressure, because it's in kilopascals, that means our answer will be in kilopascals, but our temperatures are an issue. Our temperatures are not in Kelvin. So we need to convert those, right? Just plugging in into our equation the 82 and the 15.2. My final answer is going to be to 2 sig figs because of our 82 degrees Celsius. Well, this in the calculator only came out to 3 sig figs, so I'm not going to add another one. And this one actually came out to 4 sig figs, so that's fine, right? It has to be 2. If I had to round, I would round to 4 sig figs, 2 more than I need. Now that we've got our units of temperature in Kelvin, we just need to plug those all into our equation, right? Remember, cross multiply. So our T1 of 355, right, is here. We're going to cross multiply with our P2 that was given to us. And then that leaves us with 288.2 times P1. Divide both sides by 288.2 to isolate our variable. And remember we said round to 2 sig figs. So darn it, look at that. How about that is our answer instead. I did that on both of the last problems now. Anyway, so 250 kilopascals is 2 significant figures. That's it. Move on to the homework. You got 4 of these to do and turn it in. Make sure you look at that grading rubric, turn it in as a PDF document or a Word document, and model your work just as I've done. Equation, plug in the values, answer with units and sig figs, and state what you're solving for.